All right, I'm finally getting around to doing these last two problems. I think it's two of them. Yeah, two of them. They just look similar. And this little acid-base thing. Now, these are called invader problems. So invader problems are when you add a strong acid or a strong base to anything that we have studied in this unit. So it could be a strong base added to strong base, or strong acid added to strong acid, or a strong acid or base, or usually a lot of times it's a buffer or salt. But anyway, so you're thinking of the strong acid, if you use that as a H+ ion invading, or if it's a strong base, then it's going to be the hydroxide invading. So to begin with, this is the one where we have to work in moles, stoichiometry, moles, that type of thing at the beginning. And then after we see what's left over from that, then we go kind of to what we've usually been doing with some of our other problems. All right, so with all that being said, let's see if I can get my mind to work through one of these. I bet you're all going to be happy to quit hearing my voice for a while, huh? After Monday, I'll give y'all a break. All right, so we got, we're adding a sodium hydroxide and mixing it with acetic acid. This one looks a little different because we don't have a salt in it like we would sometimes in a buffer system. But what you have to realize is that probably if we showed a buffer system with the weak acid and its salt, that it probably would be sodium acetate. Well, we already have the sodium here, so that's why it looks a little bit different on this. So since I know I'm doing an invader problem, I'm going to go ahead and figure out how many moles I have of each thing, because that's what I have to work with. So remember, you're just going to take your molarity and you're going to multiply it by your volume in liters, 0.125 in this case. So I'm going to have to probably take it. So that means I end up having 0.0625 moles of my sodium hydroxide, which really out of that, I'm interested in my hydroxide. Since it's a base, that's going to be my invader. And then over here, I would do the same thing, 0.125 times 0.5, and that's going to give me 0.0625 moles of that one also. All right, so let's see where we go. So since I have a strong base, my invader is going to be my hydroxide. Okay. If it would have been acid, then it would have been the H+. Now, when you're at this point, you have to kind of think about what you have. So I have acetic acid, which my acetic acid, you've got to know some of your polyatomic ions. If not, might get lucky and be able to find them somewhere else in the test. And then I'm going to have, so that's my weak acid, and then I'm going to have its conjugate, which would just be the acetate. Okay. So you got to think, which one is it going to react with? We said if we had a strong acid, which would be the H+ part, it would react to this, and it would force that reaction back. But since I have a hydroxide, it's going to react with this, specifically the hydrogen on that weak acid, to form water. So I'm going to add that in. And that's going to give me some water. And then my C2H3O2 acetate, or you can think of it as your conjugate base. All right, so now I kind of going to take this reaction and put over here. This is similar to a rice table, but we're going to work in moles. HC2H3O2, and this would be C2H3O2 minus. I was working some other problems, and this is kind of a pain to write. So I saw where they did this as the acid for acetic acid, and then they just did this for the acetate ion. Maybe a little bit of time saved. All right, so we start off, we said with 0.0625 moles of this. And right now we're working in moles. And then we had our acetic acid, that also happened to be 0.0625. And then we didn't have any, at that point, we didn't have any of our conjugate. So my hydroxide and my acetic acid are both going to decrease. They are on a 1-to-1 mole ratio, and I had the same amount of moles, so they're both going to react. This doesn't become a limiting reactant problem where I'm going to have a little bit left over of one or something like that. If that was the case, then you're going to have it, if that happens, you would have some hydroxide left over at the end, and it actually becomes an easier problem. This is going to have that many moles added to it. So when I end up, I have none of these, I have none of this, and I end up with 0.0625 moles. And we can think of this as our salt. Okay, remember, I know it looks a little bit different, but that would be our salt. This would be our hydroxide. This would be our acid. In this case, all we have left is our salt. So at this point, it becomes a salt hydrolysis reaction, which we've done that before too. So I'm going to move my thing up a little bit. So, all right. So we said now it becomes a salt hydrolysis reaction, which means that that acetate ion will hydrolyze or break the water apart. So I'm going to write that reaction. And we said it's a conjugate base, so we have to realize that this is a base reaction. We know it from our definition. Base accepts a hydrogen, and also because we have some hydroxide at the end. So this is a base problem. And up at the top, they gave you a Ka. You didn't get a Kb. Another thing that changes here is that when we start working in these, now we're going back to concentration, back to molarity, which is what we do most of our things with. So I need to figure out my concentration of this acetate. So we said there was 0.0625 moles left. And remember, molarity is moles per liter, and that is total liters. So I had 0.125 of my sodium hydroxide and 1.125 of my acetic acid. So that gives me a total of 0.250 liters, which is going to give me 0.250 molar. I'm going to kind of circle that. I don't know if you want to do that, probably not, so they don't think that you think that's the answer, but I'm going to get lost if I don't. Other thing I said we got to have is we need a Kb because this is a base reaction. And I had a Ka. All right, so 1.8 times 10 to the negative fifth. That's what they gave me. So that now gives me a 5.56 times 10 to the negative 10th. All right, so now if I write my Kb, and remember I'm writing it for that reaction, it's going to be hydroxide concentration times my, I'm going to put it as acetic acid concentration divided by my acetate. Divide this, yes I did. I got myself confused there for a minute. All right, so that's what we got. We don't have any of these two at this time, so that's going to be my usual x squared. And then on the bottom, I'm going to have my 0.250 molar minus x. And remember, you are going to want to make like some little note, don't just not ever put it. X is negligible. So I know I'm misspelling in this subtraction or something like that. I don't think it needs to be a big explanation, but put something like that. So now I'm going to take my value, 5.56 times 10 to the negative 10th is going to be equal to x squared over 0.250 molar. I'm going to work through and find out my x is 1.18 times 10 to the negative 5th. And I need to remember that this is my hydroxide concentration. That's not my H plus concentration. So I still need to go through all those little bitty steps that I'm going to go through because I have done all the hard work. I'm going to say my negative log is going to be 1 times 10 to the negative 5th. And that's going to give me 4.928, which is equal to my POH. I'm going to make sure they know that I know that. 14 minus 4.928 is going to give me 9.072, which is equal to my pH. That I am going to circle, and I'm going to realize that if I go back up to my concentrations at the very beginning in my volumes, it was 3 sig figs. So that is why I have 3 sig figs right here. All right, so that is an example when you have some salt left over, which is really more work than if you would have had some hydroxide left over, or if it was a different type of reaction, some acid left over. All right, so let's flip over to the back and get that one done pretty quick. All right, so we got some, now we got 200 mils of 0.5 molar, and that 200, because it doesn't have a decimal behind it, is really only 1 sig fig, but I'm going to do it like it has a decimal. It's a pain to have 1 sig fig. I feel like that's something they'll probably stay away from. All right, so I'm going to do my real quick. I'm going to change it to moles. So 0.2 times 0.5 is going to give me 0.10 moles of my sodium hydroxide, and this is a strong base, so that means my hydroxide is going to be my Invader, probably misspelled that too. I'm glad I'm not taking a spelling test for Monday myself. 0.5 gives me how many moles of that? Let's see, that one was 0.1, and I think this was the same as before, so 0.0625 moles. Yeah, that didn't change. All right, so I said my Invader, because it's a strong base, is going to be hydroxide. And once again, the hydroxide is going to react with the intact acid. You don't need to write this step. I'm just keep showing you. That is what would happen. And I would end up with some H2O. And then once again, my acetate ion, I should have, since I abbreviated there, I should have kind of abbreviated there. I could think of that as my conjugate base. Think of it as my salt. All right, so I'm going to do my same thing here. And I'm going to say this is my, and this is my acetate. And then I had some water, but we don't have to worry about that. All right, so my initial moles on this was 0.10. And I know right now my sig figs may not be correct. I'm going to clean all that up at the end. 0.0625 and none of this to begin with. Okay, now this one's a little bit different because I have different amounts. So in this case, my acetic acid is my limiting reagent or my limiting reactant. It's still a 1-to-1 mole ratio. I can't use all of that 0.1 because I don't have enough acetic acid to work with it. So all I have is 0.0625. So I'm going to subtract that. And I'm going to subtract 0.0625 moles. And I'm going to add 0.0625 moles. So when I am over, here I end up having 0.0375 moles, nothing here, and over here I had 0.0625 moles. Now, in this case, I had some hydroxide left over and then I had the salt. At this point, if I have hydroxide left over, or if this was, instead of sodium hydroxide being added, if this would have been one where hydrochloric acid would have been added and I had some hydrogen ions left over. If I have those left over, they are going to override anything that that salt could do as far as pH. So it actually becomes an easier problem where I can just use that formula to get my pH negative, which one am I doing? Yeah, negative log. So it's going to be an easier formula. It's going to be an easier problem. All right, let me move that up a little bit now that I've. All right, so now we're down to here. So we said we got some hydroxide left over. So once again, I'm going to have my acetate ion plus my water is going to give me some hydroxide plus my 2. This is a strong base that's coming from sodium hydroxide right here. And we said that was left over. And we had 0.0375 moles. But once again, I need that in molarity, not just in moles. So I'm going to divide that by the total volume, 200 milliliters of sodium hydroxide, 125 milliliters of acetic acid, 325 liters, and that's going to give me. All right, so if I can simply take the negative log of my pH concentration, negative log, and that's going to give me 0.939, which I have to remember is my pOH. So 14 minus 0.939 is going to be 13.061. So that is my pH that I'm looking for, and I'm going to circle it. All right. And once again, 3 sig figs, that's all that counts. The numbers behind the decimal, which matches up with my beginning. All right, and not going through another problem, but I did just kind of want to say, both of these have happened to be bases. Let's say that if we would have done a strong acid instead, so that would have made my Invader. I feel like I'm really spelling that wrong. My alien, maybe I'll start calling it my alien, my hydrogen ion. So now if that is my Invader, your Invader always becomes a reactant in your problem. You have to remember that it's going to react with the acetate ion to go back to form that weak acid. This is a weak acid. It does not ionize. It would like to stay, it's more stable. I shouldn't personify it. It's more stable together as an acid than it is whenever it ionizes. So what that is telling you is that the attraction between the atoms is in the molecule is stronger than the attraction for water with water in these different ions. So that is why it will not ionize. Where something like this does ionize. So what that is telling me is that water has a stronger attraction for these ions, and the process of solvation is stronger than hydrogen and chloride had for each other to stay as an intact ion. Because remember, if this ionizes, we got a bunch of water molecules that come around it. That's what we talk about when something goes into solution. And they have to orient themselves. This is my negative ion. I got to have my positive hydrogen this way. If this is my positive, I got to have my negative oxygen this way. Okay. Remember, your anion is going to be larger than your cation, especially in this case, because it's gained some electrons. So that may change the size a little bit, but what it really does, gains electrons, has not changed its number of protons in its nucleus. So now it cannot draw those electrons in as much. And so that ion becomes a little bit larger. All right, thanks a lot. See y'all tomorrow.